Okay, now I'm going to stream the video on YouTube. If you all agree, this will be a public streaming.
Sure. I mean, I agree personally.
Okay. And perfect. We are on air. Now I just have to. Okay, I'm sharing the screen. You should be able to see my screen and hear my voice.
Yeah.
Okay. Okay.
Tu veux que je le fasse ou tu...
Non, je vais le faire.
Oui.
Est-ce que ça marche? Okay. Can you hear me? Yes.
Well.
Okay. So welcome to Valentina, to Gloria. Pietro is with us here. Marco is there, and Philippe Robert. Where is Philippe? Philippe has just escaped, but he should be back just by my side. So we would like to ask Valentina GARIBOTTO, would you accept to chair this jury, this committee?
Of course, happy to chair the jury. This
okay,
very
that's
distinguished
wonderful.
Jury.
Okay. Yeah, because we already asked Gloria to write a report, and as well as Pietro, and so it's now a pleasure and a privilege if you accept to do this. So I will give you the floor, and you just have to present very briefly the jury and give the floor to the candidate for 45 minutes. Yeah.
Okay, sure. So thank you for inviting me for this jury and to this chair task. It's a pleasure for me to be here. The jury is composed by the directors of Luigi Antelmi's Ph.D. work, Nicolas AYACHE, and the co-directors Philippe Robert and Marco Lorenzi, and the reviewers, which contributed with the reviews, Gloria MENEGAZ from Verona and Pietro MICHIARDI from Sophia, Antipolis. Luigi, and tell me, the floor is yours to present your work. You have 45 minutes, more or less, what remains until 2:45, and then we'll go with the questions.
Okay, thank you very much. Can you confirm once again that you hear me and can see me?
Well.
Okay, so good afternoon. It's a pleasure for me presenting today the work done during my PhD studies in the EPION team of Inria. It is about the topic statistical learning on heterogeneous medical data with Bayesian latent variable models. And we will show applications into the neuroimaging dementia studies. Before starting, allow me to thank the people present here today, all my thesis supervisors and all the jury members, and also all the public following this event online. And without any further ado, let's start. Dementia is a syndrome with an important cost for the patients because it affects many important aspects of their life. It involves a human cost for families and caregivers too, and it has a huge impact on society. And projections show that this disease is going to, this syndrome is going to affect our society even more in the next decades. The Alzheimer's disease is the most common cause of dementia, and we will this thesis will be about this disease. So the research, given the huge impact on society, researchers has come out, and given also the difficulty in making a diagnosis of Alzheimer's disease, researchers have looked for the hallmark of this disease with different and powerful imaging modalities. For example, to measure the concentration of the amyloid protein in the brain, which is abnormal in the diseased brain, and it is the hallmark of the Alzheimer's disease. And unfortunately, this can be confirmed only with post-mortem biopsies. Another protein builds up in the abnormal, in the diseased brain, which is the tau protein, and imaging to measure this content, the content of this protein is necessary for the diagnosis, but still not it's necessary to differentiate that diagnosis, but still not sufficient to target the AD. We have another biomarker, the glucose metabolism, that can be measured again with the positron emission tomography scans. It is used to measure the uptake of glucose from the neurons. It is impaired in the diseased brain. It is the typical pattern is an impaired metabolism in the temporal part, in the temporal lobe of the brain. Lastly, all these impairments lead to neuronal death and to atrophy of the brain volumes, and ultimately to cognitive impairment that really affect the patient's life. Given the complexity of the disease, combining the biomarkers may help in improving the diagnostic accuracy. But there is not only neuroimaging, there are not only neuroimaging biomarkers, there are many more, and the research show that by combining results from the imaging with the genetic data, it is possible to quantify the relationship between genes and brain atrophy. Or by combining sensor and neuropsychological evaluations, it is possible to reduce the uncertainty in the assessment of the status of the patient. And lastly, there are new possible relationships to be explored, such as the relationship between the gut microbiota and the brain. So you understand now that how important it is in this context to model the heterogeneous biomarker in a jointly manner. For example, in the recent study published a few months ago, the authors linked the brain microstructure measured through diffusion tensor imaging to neuropsychological assessment, and they did it with the partial least square method that works by projecting the original data into a lower dimensional and simpler latent space, where a correlation between the two modalities is expressed. And so this is a method for automatically extract features that help in discriminate the subjects, in this case between a subject with normal cognition and subject with cognitive impairment. There are many other multivariate methods for the joint modeling of the heterogeneous data, but they are usually made to model two modalities at a time. And they usually do not provide uncertainty quantification. Why it is important to model the uncertainty? The most common models are deterministic ones, it means that they give you point estimate, for example, for your biomarker given the input data. But it is as well important to quantify the certainty of these predictions so that we can better judge which prediction we can trust. And with a probabilistic model, with many probabilistic models, we may even choose which one of them gives the least uncertainty and use it as a consequence. An example of such a model is the Variational Autoencoder. It's a nonlinear data modeling framework composed by a discriminative part, an encoding part, like the partially square method that we saw before, that takes the data and projects it into a lower dimensional latent space, but this time in a probabilistic manner with point estimate and quantification of uncertainty. And it has also a decoding path that goes in the other way around from the low dimensional latent space back to the space of the data, and allowing us to reconstruct the original data and to synthesizing new data also. And there is a whole active area of research around this framework, for example, to provide good parameter initialization or to get a more informative latent space. And at the beginning of my thesis, this model was meant to modeling single biomarkers, single data modalities. Together with the quantification of uncertainty, another desirable property of a model is the one of sparsity. And I will illustrate a simple example here. Let's assume a simple model made with two parameters, like, for example, a linear model with parameters being the slope and intercept. And the way that we found the parameters given the data is by minimizing the discrepancy between the data Y and the prediction of the model. In an unconstrained manner, the solution gives us some values for our parameters, but there are reasons, for example, to constrain, to regularize the solution, because, for example, you may need your values to be in a certain range or to have a physical meaning. And there are further ways to constrain the solution such that you may get rid of some parameters or even more. Think about the case where models have millions of parameters, like in the new deep learning framework. So it's a good property to have to discard many parameters without compromising the capability of the model in making predictions. So this is what we call a sparse solution, a solutions where few parameters plays a big role in the model predictions. And of course, this is desirable also in a probabilistic framework. When jointly modeling many biomarkers together, it may happen that some of them may be missing for some subject. And the reasons are maybe random because the patient drops out from the study or because the quality control of the imaging fails, or for non-random reasons, for example, where you gather data together from different studies that have different protocols. So you end up, when you count how many data do you have, you end up with tables like this with many missing places. But it's a pity not to be able to use the totality of the data that we have because they are costly to acquire. And the usual way to deal with this problem is to ignore it. That is to discard the whole set of measurement from a subject if even one of them is missing. So we can do for sure better than this to use all the available information. Another problem that comes when we gather together data from different studies, different data sets, is that there is a mismatch because of what is known as domain shift bias. So we see here that when we take a structural MRI measurement from two studies on depression, in the region where there should be an overlap between the two studies, we end up with a bias, and not only on the mean value, but also on the dispersion around the mean value. So it is important to use harmonization methods to match the usual statistical modeling hypothesis of independent and identically distributed data, and to have also more data to be fitted in your model to increase the modeling power of the model. So far we're seeing many modeling challenges when dealing with the complexity of the dementia and of the Alzheimer's disease, and they are basically on how to jointly model all the heterogeneity of measurements, how to quantify the uncertainty, how to have interpretable results, how to have sparse results, how to deal with missing measures, and how to correct for biological biases in the data. And we try to address all these points within the context of this thesis. So in the next part, we will deal with the joint modeling of heterogeneous data with a probabilistic model, and that gives sparse interpretable results. A few minutes later, we are going to extend, I'm going to present you how to extend this framework to allow to use all the information available when gathering data together from different data sets. I will show briefly a benchmark for state-of-the-art methods for correcting for the domain shift bias. And before concluding, I will briefly present the software that came out of this thesis work. So let's start with the first part. From a joint, for modeling jointly heterogeneous data, a way to address the problem in a probabilistic way is through a latent variable generative model, where we assume that a simple variable z, lower dimensional interpretable, is the source that generates all the observation around a particular phenomena. And an interesting thing that can be done with such a model is to start with the data and compute the latent space from them. So to compute the posterior distribution P of Z given your observations. And this is very similar to the variational autoencoder that we have seen in the introduction, with the encoding part that projects the data in the latent space and the decoding generative part. Computing the posterior distribution, so computing the projection, is usually intractable. And we will take a look at the variational autoencoder on how the intractability of the computation of the posterior distribution is solved there, and apply the same reasoning to our case. The exact solution for the encoding part of the variational autoencoder is intractable, is usually intractable because it requires to compute complex integrals that are numerically cumbersome or not analytically, the computation can be analytically unfeasible. Fortunately, we can rely on the variational approach where we settle for an approximated solution, and we do it by minimizing the distance between the approximation that you want to compute and the real posterior distribution. This distance is measured through the divergence of Kullback-Leibler. And by using the definition of this divergence and the definition of expected value, we can transform this objective and derive the quantity on the left side of this equation that is called the evidence lower bound. This quantity is a quantity that we can compute, and we can show that by maximizing the evidence lower bound, we can as well minimizing our original problem, so we can recover the approximate solution that we are looking for. The lower bound is made up with a likelihood term and a regularization term. So in the likelihood term, we require our solution to be the one that best explain our data, and with the regularization term, we are required to behave nicely, to be as close as possible to the prior distribution that you think your data comes from. How does apply to our case? In our case, we have many candidate solutions, many encoding distributions, one distribution for each data modality. And we can require to all of them, on average, to be as close as possible to the true posterior distribution. With the same mathematical reasoning, we can derive a lower bound with the likelihood term and the regularization term. And you see what happens here when we optimize the lower bound. We require to every single encoding distribution to be able to reconstruct all of the other modalities, including itself. And being this quantity, the lower bound, a lower bound to the model evidence, we can use it also to select between models and choose the one that gives us, for example, the least uncertainty. We can optimize this model. First, we have to define the encoder and the decoder, and in our case, we choose it to be parameterized through Gaussian distributions, where the mean and the variance are learned as a function of the input and the model parameters. So we started with a problem of joint modeling that was intractable, and with the variational approach, we made it tractable. Let's see how can we use the lower bound for model selection, for example, for tuning the number of latent dimensions, which is, as a model designer, you have to choose ahead how big you want your latent space is. And we generated for this experiment ourselves ground truth data by changing the number of latent dimensions in the ground truth. We fitted our model as many times by increasing gradually the number of latent dimensions, and we find out that we have an optimum of the lower bound or when we hit the true number of latent dimensions used to generate the data. So this is model selection in action. It is a long process, as you may understand, because it requires to fit your model many times with your dataset. So this is a good place to introduce the sparsity, because it can help us in reduce the number of latent dimensions automatically. How can we do that? It's actually very simple, because what you have to do is just to change the way we parameterize the posterior distribution. In the classic formulation, we have a distribution where the mean and the variance are independent on each other. When we go into a sparse setting, we use what are called in the literature dropout posterior, where the mean and the variance are linked through a quadratic relationship and a parameter alpha that has the meaning of odd ratio. So it allows us to compute the probability of dropping out the ith latent dimension. But still, how does this promote sparsity? What's the mechanism behind it? Well, think about the regularization term. There, in that term, we have the regularization that it pushes the mean of the distribution towards the prior, and in this case, towards the zero. And with this parameterization, also the variance goes to zero very fast, actually, with a quadratic term, and we end up with the ith latent dimensions to be collapsed to the zero. This is a direct distribution in the zero. But remember that there is also the likelihood term that plays a role in the optimization. So at the end of the training of your model, the equilibrium between these two terms is reflected in the parameter alpha and also in the probability of dropping out the ith latent dimensions. So in practice, when we fit a ground truth multimodal scenario with 20 latent dimensions, we just have to sort our latent dimension by their probability of dropping out, applying a threshold, and in this case it's striking. And we see that with this threshold, we can recover the true number of latent dimensions used to generate the data. The ordering, the sparsity by itself, but also the ordering increase the interpretability of the model, because right now we can concentrate ourselves to interpret few latent dimensions, to find the meaning for few latent dimensions and in a certain order. So we can look at one parameter, try to describing it, if it makes sense, etc. And this is a way also to compress the models, because we can prune the dropped latent dimensions, but remember that there is also the generative part in this framework So we can prune also all the associated generative parameters. Let's apply this model to a real case of to the neuroimaging data. In this case, the data come from the ADNI, the Alzheimer's Disease Neuroimaging Initiative, and we collected data from subjects at different stages of the Alzheimer's disease. We collect them in four modalities. The first one is the clinical modality composed by age, education level, mini mental score examinations, and other measurements that are relevant to assess the clinical state of a subject. We took structural magnetic resonance imaging from the T1 MRI. We used the software SPM to compute the gray matter density in the brain, and we averaged this gray matter on the AAL atlas composed by 90 brain regions. So from one imaging modality, we obtain 90 measurements from the MRI. The same process, we applied the same analysis to the FDG PET to measure the glucose uptake in the brain, and to the amyloid PET to measure the buildup of the amyloid protein in the brain. And we fit our model with the sparsity constraint, and we used for it a linear parametrization for the encoder and the decoder. We see that when we fit the model with 16 latent dimensions and we apply the threshold of 0.2, we can keep 5 latent dimensions. And if we plot the first two ones, one against the other, so we encode the data in our latent space and we select the subspace made from the first two latent dimensions, we see a nice unsupervised stratification by diagnosis, and on the same latent space, on another direction, a stratification by age. And the same result is obtained on the testing holdout set. We can look also at the generative parameters and see that all jointly make sense in the clinical context of Alzheimer's disease, because there is, for example, the inversion between the inverse relationship between the mini mental score and the clinical dementia rating scale, altogether with the increase of the amyloid uptake and the decrease of the gray matter density in the brain. So all of these make sense in the clinical context. You see that we can use the latent space to stratify and to discriminate the subject. And we run a benchmark where we compared our framework with other variational autoencoder based frameworks. And we see that the classification is better within our framework, and we have a tie with the variational autoencoder setting. We can do trajectory sampling on the latent space and simulate the aging process. For example, we can simulate a normal aging process and an aging with dementia process. And we see that when we generate data starting from these trajectories, the observations on the dementia trajectory happens to be pathological in all the cases, in the MRI, in the amyloid, in the FDG, and while in the normal case, we have a healthy status of the imaging. Again, all of these make a lot of sense. We can use our model also to impute missing biomarkers or to explore the relationship between biomarkers. And in this case, we changed the value of the mini mental score in input, and we computed the prediction for the MRI, and we see again the relationship between the atrophy and the lowering of the mini mental score with a particular involvement of the temporal part of the brain and the hippocampus region. To summarize this part, we presented the multi-channel variational autoencoder framework. It allows a probabilistic joint modeling of heterogeneous observations with interpretable results. It can be used for data imputation, simulation, and classification. And at the time it was presented, we presented it, it was timely and relevant for the machine learning community. Of course, this is not, it's far from perfect. because it needs, for example, all the data modalities to be there in the training phase. So it cannot really fully leverage on data coming from multiple data sets because of the problem of missing modalities. And this is why we extended this framework to be compliant with the multitask setting, where we associate one task to one data set. The motivation, well, we briefly recall is because when we want to increase the sample size by putting data together from different data sets, we have to deal with the problem of missing modalities. If we search in the state of the art for possible solution for this, the word multitask is in the first ranking, and we selected here I will show just a brief very brief literature review. For example, with the meta-learning approach, the authors propose to have many nearby models as tasks. What does it mean? That they propose a general model with the general parameters that can be adapted easily in few learning steps to model many tasks, many data sets altogether. So at the end, we have still 3 different models, but the parameters are close enough to each other. It's an interesting concept, an interesting approach. Another approach, for example, the stage learning for classification, is very interesting also. Here we see the scheme for a network that takes as input imaging modalities, MRI, PET, and genetic data, and gives as a result a classification for the subject. Why it is interesting? Because it allows, it's made in such a way that you can train different stages of this network based on the data that you have. For example, if you only have 2 modalities, you can train the second stage. With 3 modalities, you can have the first stage, and it keeps going like this with the combinatorial complexity. There are other methods that can be used, for example, the noise autoencoder, the embrace net, and surprisingly also the classic K nearest neighbor method that it has been shown sometimes to be superior to autoencoder-based methods. So we take this concept and we apply it to our framework. We do it by proposing as many models, as data sets, but in this case, for example, where we have 2 modalities that are not present in dataset 1, we freeze the parameter of this model, and we feed just the parameters of the part of the model that we have. And we can do this with all other instances of the model, taking care of sharing the parameters of the common modalities between all the models. By doing this, by computing the cost functions for all the models and gathering together all the parameters at the end, we end up with a multi-channel model that now has been trained on all the data available in our dataset pool. How does this model behave? So we're modeling a real case scenario where we have data from different datasets with missing data. So we took data this time not only from the ADMI but other neuroimaging dataset that had studies made for studying the dementia. We processed the imaging in the same way that we showed earlier. This time we applied the harmonization method called COMBAT to make the hypothesis of IID observations. And we will come back on this method later on in this presentation. We ran a first experiment. We hold out the ADNI2 dataset because it gives us the possibility to measure the data imputation capabilities of the model on all the modalities. And we see that within our framework, we reach a better, we reach a lower prediction error on imputed data in a significant manner. We ran other experiments for feature prediction in different conditions also. For example, when the training and testing data come from the same data set, And when the training and testing data come from different data sets, and again, we measure the reconstruction error. And we see that within the multitask extension of our framework, we have better prediction. So the error is inferior to the framework without the multitask learning scheme. And we also made the experiment on a pure multitask condition where the train and test data come from all the dataset pool. And we see that we reach even further lower error when predicting with respect to the previous condition. We also run experiments. Of course, this is just a snapshot because similar results are obtained with the other imaging modalities, the other PET imaging modalities. We did the same experiment with a diagnosis prediction model. In this case, we changed the decoder and we used a Bernoulli decoder to model the binary classification of the different diagnostic groups. And again, we see that within the multitask framework, the accuracy of predicting the diagnosis is higher. And in the multitask learning set also, it is higher, is compared. So to summarize this part, we extended the multi-channel framework and make it able to learn from multiple data sets. So it's not anymore necessary to have complete observations to fit the model. And it has the limitation that we've seen before, that it requires an external harmonization tool, a method to reduce the domain shift induced bias. This is why we also wanted to benchmark different harmonization methods. We want to be sure to have selected the right one. And as combat is not the only one, so we look out in the literature and we found out that there was a recent extension of combat and also a nonlinear version of the variational autoencoder, a particular version of the variational autoencoder that allows to model the domain shift. So in this benchmark, we have a linear method, a linear correction method widely adopted by the neuroimaging community. Its extension to a multivariate setting where there is a further harmonization of the covariance of the data sets and the nonlinear method to compare with. How does the three method work? If you apply combat to the case illustrated in the introduction, we see that it actually it harmonizes the data. So we see that after the harmonization, not only the average values are similar in the overlap region, but also the dispersion around the mean is similar. So this is what a good harmonization method does. It removes the bias induced by the study, by the data set. It reduces the unwanted bias by keeping the biological variation in the data. This is combat is not a multivariate method, and we can see it from, for example, if we plot correlation matrices from data coming from different data sets. We see that in the non-harmonized data, there is a difference in the correlation pattern between different data sets. So we can tell from which data set our observation come from. And in the combat harmonized data, we can still tell from which data set the data come from. So it's not removing all the information of the data set. COVBAT, the extension to the multivariate case, instead, it reduces this, this effect. And we can see it visually from here. The domain invariant variational autoencoder also can be used to remove the domain bias, because in this example, we can see that it can model the domain, for example, the background color due to the staining procedure of red blood cells from the biological variation. So we can put to zero the domain and we can reconstruct only the variation that we are interested in. And we see that in the linear case of the DIVA and the correlation matrices are indistinguishable one from the other. So apparently, it's removing the data set information from the data. But we see at the same time that it is the data structure that was originally in the data is not anymore there after the correction with DIVA. We can recover a bit of correlations with the nonlinear version. DIVA 4 means that we use 4 layers as for the encoder and for the decoder part of this method. And here we have the numerical values from what we see visually. So with COVBAT, we have a reduction of the difference between the data set with respect to the unharmonized data. With DIVA, the reduction is even lower, but this is a spurious result because we are destroying actually the original data structure. Of course, a visual benchmark is not enough to choose which method is the best. So we run also a quantitative benchmark by generating data for a classification task with the sklearn function. We bias ourselves, our data, with a linear transformation and a bias specific to each data set, and then we harmonized this biased data with the 3 methods. In order to tell which one of it is better, so we train and test a classifier on harmonized data, and as we explained before, if the harmonization worked, we should be able to still to classify the variation that we are interested in. For example, we should be able to discriminate the class label, while we should not be able anymore to distinguish from which data set the data come from. This is the result on the label classification. Here we show the accuracy in predicting the label. And we see that when the data are harmonized with COVBAT of combat, the results are pretty much the same in all conditions, except when the number of features of your data is higher. In this case, COVBAT is preferable. And DIVA is generally bad, although there are some cases where it is superior to this state of the art. In the dataset classification experiment, in this case, the lower the accuracy, the better the harmonization method, we see again that combat and COVBAT are basically aligned. And there are some cases for the DIVA method to be better than it appears to be better than the state of the art. But as we said before, probably this is just a spurious result because the DIVA is removing more than just the dataset information. To conclude this part, harmonization method, combat and COVBAT are generally aligned between them. The latter should be preferred when it is important to have a multivariate method to harmonize covariances between datasets and when the number of features of your dataset are higher. Still, be cautious with the domain invariant variational autoencoder method because we noticed an important level of data corruptions. So more research is needed on it to understand when it can outperform the state of the art. Okay, now before the conclusion, I just want to present you briefly the software that came out of the work done in this thesis. So if you can summarize this thesis, I think that this is the correct way to do it. We took the state of the art, the variational autoencoder, and we extended it to model many modalities in a jointly manner. And then we further extended this framework to be able to be trained with all the data available without discarding any useful information. And this inheritance property can be very simply and elegantly implemented with an object-oriented programming scheme. We leveraged on the PyTorch deep learning library for many basic functions that helped a lot in the building of the models. And we can see the inheritance scheme here. So with the arrows. From the main PyTorch model, we built our variational autoencoder class, and the user of this package can also define his own variational autoencoder by just re-implementing the architecture part. So we are taking care of computing the loss function, optimizing it. So you really have just to think about its architecture. And on this other side, we see also the multi-channel framework that it consumes many variational autoencoder. and the extension, that the multitask version that inherits most of the machinery from the previous module. So you see that everything fits well in an object-oriented programming scheme. We enriched the package with some plotting utilities for checking the training convergence, for plotting the latent space and stratify your subject, for example, or for choosing the right dropout threshold. And I was lucky to have the chance to present this work in a winter school workshop early this year. I have to thank my supervisor, Marco Lorenzi, to give me the opportunity to disseminate my work, and also the other members of the Epion team that collaborated and made a nice presentation out of all the many other interesting things that were presented that day. To conclude, the contributions of this thesis are as such. We presented the multi-channel variational autoencoder framework, so to model in a probabilistic way the heterogeneity of the data that comes in the biomedical field. It gives interpretable results. We extended it to a multitask setting to learn simultaneously from multiple data sets. We provide simple guidelines for choosing the right harmonization tool. And then finally, we made a software package out of the work in this thesis. There are also, of course, this work is still in the beginning, and there are perspectives, interesting perspectives, I think. For example, one we may ask in the context of the modeling jointly imaging modality, what is the added value of the PET imaging with respect to all the other biomarkers? This is a question that with our model still we cannot solve because it requires the introduction of a new variable that is specific to the data modality. So in the future, probably it will be the case to explore the disentangled multi-channel variational autoencoder. Or also to avoid recurring to external harmonization methods, to embed the harmonization within the variational framework itself. Other perspectives, for example, temporal modeling for longitudinal data analysis, it may help to disentangle subdiagnostic types based on the evolution of the pathology. Or it can have industrial applications anywhere it is needed a joint analysis of data coming from different sensors. And I think personally to the automotive industry with the self-autonomous, self-driving cars, or also in the home safety for monitoring frail people through cameras, wearable sensors. And I think that there is also a contribution for the digital twin framework where we can provide personalized models and by promoting a data-driven and objective approach to the healthcare. And with this, I would like to thank all the Epion team and my supervisors and all the people that make this thesis possible. Thank you.
Thank you, Luigi. Excellent work and excellent timing, actually, to the second.
Really?
So I don't know if we clap or if we go straight for the questions. The floor is now open for discussion. I invite the members of the jury to start questioning. Is there anyone who dares to start?
So the tradition is to ask first the reviewers, and usually in the order of the one which is the most remote from the location of the thesis. So I guess it's not Pietro.
So it will be Professor MENEGAZ, then who has to start?
Claire, you're muted.
We don't hear you. Yeah, you're on mute.
Now, okay. So thank you very much. Thank you, Luigi, for the very nice and very clear presentation, where the minor doubts that remained after reading of your thesis were actually clarified. So you did really a very, very, very big work. I would like to congratulate with you because you faced the problems that we can encounter along the whole chain of processing of this data. So from the issue of dealing with multimodal data to the multitasking, to the different optimization issues that we can encounter, and also because you proposed a tool that allows other people interested in the problem really to put the hands into it and to start implementing, building on your results. So I would really like to congratulate you with this for this very big amount of work involving both theoretical and practical aspects, which is actually rare. So there are maybe many potential issues that could be discussed because it's of the dimension of the work. And for instance, one that comes into my mind is that you make the assumption that the variables are conditionally independent, while we know that the data source basically is the patient if we constrain to the single data set case. So this independence across the sources of data might not be so well verified. So how would you comment on this?
Okay. Well, it's actually it was one of the first questions that I asked myself in the beginning of the development. But then the solution, it was in front of my eyes, that basically it's true that all the modalities are all dependent because there is a single subject that generates them, but they are dependent as long as the subject is unknown. Once you know the subject, once you use the encoding part of the method to compute that distributions, that you don't care anymore about these the independencies, because it's now the latent variable is not anymore latent. It is known. It's observed, and the relationship between the observed values to observed values doesn't take into account any other possible values. So there is it's the concept of conditional independence. So the observations are independent given a latent variable, unless that latent variable is actually not latent anymore but is known, because you can establish the relationship between the generative part, actually, with the generative.
Okay, so it's not really an issue.
No.
Okay.
Within the framework, no. If we add, for example, if we add the temporal modeling, that it is an issue, because in that case we cannot. We have, for example, for a single modality, 2 time points that are not anymore independent. So for the same modality, there is this problem that 2 measurements coming from the same subject are correlated.
Exactly.
This is why this model is only cross-sectional. It's not longitudinal, and actually temporal modeling is something that is in the perspectives. But as long as the modalities are different, given the same latent variable, given that this latent variable is observed through the encoding, then the independence is not anymore an issue.
Okay. So another question would be like this. So you can predict the missing views of your data using your model, but to which extent you can be confident about the accuracy of this prediction, actually?
Well, it's the probabilistic framework that gives you also the boundaries. No? In this presentation, I showed only the average prediction, but you don't have to forget that the output of the model is a distribution, is not a point estimate. So from that distribution, I showed just the expected value. You can as well simulate, you can sample from that distribution and simulate the possible scenarios that are around that mean. So you can quantify the uncertainty by sampling those distributions. You can sample in the latent space, the encoding and see the variation, and sample also in the decoding part. And if I may add, there is a nice way to show the sparsity, actually, that is, for time reasons, I haven't showed here. It's when we plot the expected value along with the prediction. So we see that the dropped latent dimensions have a large, very large variance. So you cannot tell really where this point is. And this is why you dropped it, because it is not useful for the prediction. It's too wide.
Okay. So another thing that that captured my attention reading the thesis is that you use both linear and nonlinear models, no? Like neural networks. And not always, let's say, these nonlinear models brought any improvement with respect to the linear one. So do you have any explanation about
this?
Yeah.
Maybe. We also for that, I was expecting also the nonlinear model to give better results, but I think that this has something to do with the data themselves, because of the data dimensionality is the sample size was small. We are in the range of hundreds, while typically in machine learning papers we have data sets that have thousands or 10,000 data. So probably a nonlinear model, we don't have enough data for a linear model to learn the non-linearities in the data. And this is one possible explanation. Also, no, I was thinking that probably also the data are a bit simple in the sense that we are computing, for example, averages in brain regions. And altogether with a small sample size, there is really no space for a powerful nonlinear method to learn the nonlinearities. So I guess that this is has something to do with the data.
So how would you do to assess actually the improvement that could be brought by your model in the best case?
How do assess the use of?
So I mean, if you somehow told that the limitation is due to the sample size, right? So there might be a situation where you could demonstrate that the approach that you propose also in the nonlinear implementation would bring some improvement over the linear implementation, such to guide maybe further experiments of other kinds.
Sure. Yes, well, if the data, if I'm right and the data are the limit, we need more data, and a simple way to have many data is to simulate them. So what we need to do is to come out with a simulation of a nonlinear relationship between high dimensional data. And already this is, I mean, it's not easy because I think about it, and there are many possible ways to do it. And but once we have a tool that allows us to simulate high dimensional data with nonlinearities, then we can use our model and test if I'm right and in telling that the problem is the data or not. So I think that we either.
So you're not thinking of experiment with other kind of data, but real data.
No. I'm thinking about experiment with a lot of data, but having many data in the medical domain is usually difficult because they are expensive. We can use data from other domains, for example, from the domains of the machine learning, typical domain from the machine learning community. We can use them in a benchmark the model with those, or think about a way to synthesize the data. We don't have to care anymore about the problem of the data size.
Yeah. So for instance, the UK Biobank data could not be of any help?
Of course. Yeah, it's, that kind of, in that data set, we are talking about 10,000s of MRI scan, if I remember well. So thousands of MRI scan. Yes,
Yeah.
yes, of course, it's actually would be a nice
Could
test.
be an option.
Mm-hmm.
Yeah. And another curiosity that I have is, what do you expect about the performance of your model if your data sets are very different in the size, actually in the samples? Let's say I use the UK Biobank way on side and another, maybe also local data set, and I try to exploit the whole set of information coming from the two. Is there any major problem due to the difference in dimensionality?
Yeah, there is a whole area of research on fairness in machine learning that try to solve this issue when you have a lot of data that is representative for a community and very few data that is less representative. So this actually can be a new perspective to add fairness to my model. I guess that the very naive way to deal with it is to weight the predictions, to apply a weight where your data sample size is smaller and reduce this weight. But probably this is too simple. I would rely on the literature on fairness in machine learning and start from that to see what.
Yeah. Actually, the important point is to
it's an
acknowledge.
important ethical problem. It's an important ethical problem, I think.
Yeah, but it's important also that you acknowledge this and provide some path to follow and to build upon to maybe elaborate more exhaustive and complete solutions. Okay, no, I think for now it's okay for me. Thank you very much.
Yeah, I thank you for the nice review. And should you have any question, please don't hesitate to.
I will,
yeah, sure.
for sure. Thank you.
Thank you for your question. I think that now the floor is open for Dr. MICHIARDI.
Ciao, Luigi. I hope the echo effect is not going to kill us here. Anyways, so thanks a lot for your presentation for the thesis, which, as you know, at least the first paper has been an inspiration for some students in my group. And that is very important, I think, during a PhD to produce some work that is actually read and useful to other researchers. So thanks a lot for that. So since in the group together with Maurizio, Filippone, we work quite extensively on this subject. I have a zillions of questions. These are questions that we ask ourselves. But I will try to behave and organize.
No, I will try to learn also.
I've been told that we have 60 to 90 minutes. So
yeah, there's plenty of time.
So historically, your publication is in 2019, which means you were working hard in 2018 on this paper. And as we already discussed also, by the end of 2018, some of the people started working on the topic of multimodal variational autoencoders. And so there is a new RIPS 2018 paper, then has been another from a different group in 2019. And from there, I mean, there's been an explosion of work on multimodal variational autoencoders with a lot of different aspects being considered, but maybe there is one fundamental question that has arisen, and there are debates, very debates about this, which is how do you actually model your joint approximate posterior? And so in the work you presented, essentially what you do is to take an average of one encoder per modality, and then you average them out, you have your elbow, and there you go. More generally, one could try to think about maybe a different approach. And one approach emerged, which is called the product of experts.
Okay.
And in opposition to that, another approach emerged that is called the mixture of experts, which is closer to what you. So the first question I have is, do you have any position on this debate that is still going on in the community? What is best and why?
Okay, let me. Is my mic on? Yes. Okay. So I acknowledge these these works later on because I was concentrated then. So, but we were working all on the same thing. Actually, it seems so. Yeah, the approaches are different. In my case, I keep the encoding distribution separate, so as well as they do. And then I use them separately to predict everything else. In the case of the product of experts, they multiply all the distributions, and the multiplication of Gaussian is a single Gaussian. In the mixture of experts, they use all these distributions and actually they mix them. I honestly don't know which one is better. I like the approach of the product of expert because it's computationally efficient. You just have to compute one, and then it doesn't have a quadratic complexity like, for example, my model. But there is the problem, for example, with the product of expert of, for example, one modality to put the weight on all the others. For example, if it happens that you have two encoding distributions that are very separated, and you make the product out of it, it happens to be the variance is lower, so it appears to be more certain than the experts, than this distribution. It appears to be in the middle, where nobody of the experts agree that there is the true posterior. I don't know, this is a philosophical problem because at the end we have to measure the performances. Actually, what would be useful to do is to benchmark the three of the models, mine and these two, on some scenarios. And for the mixture of experts, I guess that I tried to also train one of it. It was not easy to do it. I still haven't understood very well why, because you have to learn the modulation, the coefficient of each function, the jitters a lot. I feel that my approach is a bit simple and it works. You keep them, all the things separated, but then you force them to reconstruct everything. I don't have any preference. I should have a preference for mine, but I actually don't have any preference. There should be a benchmark. Someone has to do a benchmark, me or some other guy, to understand in which cases one is better than the other. I guess that if you simulate data from a mixer will be better. If you simulate data from a product, I don't know. They're tools. They are not. It's easy actually to go from one model to the other. So probably it can be even an extension of all these three works to a more general one. So
and there are hybrids model already, of course. Okay. The pace of publications in like machine learning is so fast that people have done everything already. So I like your perspectives on this. I would agree, philosophical question. That being said, there are some consequences on also other objectives that your work and many other share in terms of what can we do, for example, to achieve training when you have missing modalities, and
sorry, to achieve
to do the training of the model when you have missing modalities. And what I tend to like about the idea of the product of experts is that this is reminiscent of one milestone in machine learning, starting from Hinton. Then there is some more recent work from Days and Roth. It's called Bayesian committee machine, robust Bayesian committee machine, and so on and so forth. These are applied in a different context, but the idea is the same. Indeed, you have products of these different experts, an expert being P of Z given X1, P of Z given X2, and so on and so forth. And when the experts don't know, you fall back to the prior. And I think this is very powerful, especially when you have missing modalities. That when you don't know what you can do,
you go back to the prior. Yes.
And then you have, okay, pros and cons. Indeed, some say, well, if there is an expert that has a smaller variance and an expert that has a larger one, maybe we should trust that one and not the other. But yeah, it's a debate. It's a debate. And I'm pretty sure there is no silver bullet. It depends on problem-specific characteristic. What is the difference? And I agree with you when you say that the mixture of experts is a bit, let's call it unstable. They have several tricks. When you look at the source code, as a matter of fact, they obtain very good results because they actually employ a variant of the variational autoencoder, which is weighted. So the importance weighted.
Importance weight, okay. Yeah.
And this is, it's not cheating per se, but then one wonders, where are the good performance coming from? From the modeling idea, from the tricks that they implement, and so on and so forth.
Also, the KL is computed with the Monte Carlo sampling, right?
Yes.
There is not analytical. No.
So now this brings me to the second question, which revolves around the second big deal, which is missing modalities. And so the way you cast the problem is very interesting. I'm pretty intrigued by this take on multitask learning, because when you look at the literature, nobody did that. So it's very original what you did. So what they did in the literature is that they take the original elbow, they take a hammer, and they break it in many pieces, and they try to simulate all possible elbow terms with a subset of missing modalities. And this means a combinatorial explosion of elbow terms to compute. In the mixture of expert paper, they address this. It becomes, let's say, linear in the number of modalities. But what you do is completely different. You say instead, we have different tasks, and I will learn a single model for these different tasks. Now, again, maybe philosophical question I have is, would you compare to these other approaches which are more direct? You just take your elbow, you simulate, you don't have modalities, and that's it.
So you mean you simulate a data that you don't have?
Yeah, so imagine
during the learning process. So the model is still learning, it's still producing data that they are still.
So take one sample that you use for training, and in this sample, instead of saying I have modality or channels 1 to C, I have only 2 out of C or only 3 out of C, and which one? Random. And every time you simulate a data point that doesn't have all the channels.
Okay. It appears to me similar to the denoising autoencoder, where they have these dropout layers, no, that basically they are used to make the network robust to missing data, to prevent overfit. I think that it can be, I don't know if it still can be considered as a loss of data, because at each iteration you are discarding data that you have randomly, but you're still discarding some data that you have. So eventually you're using them all. So probably it's it would be interesting to introduce the randomness within the multitask framework proposed here, not to deal with missing data, but to prevent the overfit, probably. I mean, the nice thing about the all this paper, all these works that, from my point of view of a young student, is that you can reuse things that are built by others and apply to your case. And at the end, they end up being a PyTorch module. So you have the dropout modules that you can add. So why not to add instead of choosing, or also for the debate on the mixer against product. Well, let's use them all. Why do we have to choose? I don't really know how to go on this subject.
Well, let's move to a different one then. Throughout your work, you have defined a very interesting application domain. I'm not familiar with it, so I cannot comment too much. What I can comment about is some of the figures that you show. And one that is striking is this, I think you call the stratification that happens in the latent space. That is very interesting from the application point of view, but in general, it is very interesting indeed. So the question I have is, throughout the thesis, it doesn't seem that you explicitly defined what people call downstream tasks, except there, when you show the figure and you say, I can stratify patients based on what I've learned in the latent space through the encoding of the input modalities. There are some people that do not really care about latent representations and what do you do with them. They are more interested in reconstruction. For example, all the people that work on generative modeling, they are more focusing on the reconstruction. They work on celebrity faces and they try to generate beautiful images of imaginary people. And so in that respect, different kind of modeling approaches have emerged. For example, energy-based models, score-based models that are more geared towards the generative aspects of the problem. And you have some difficulties there. On Twitter, you had this storm of tweets by people saying, with a multimodal approach, you can type a text, describe an image, and the model will generate the image that comes with the text. Potentially, you can do the same thing. So the question is, why didn't you try to do something like this that is super trendy and would make you a superstar on Twitter?
I don't know. I don't know why I didn't do it. But they do it with the variational autoencoder based procedure because
that's why I'm asking.
The wire results are blurry. You know, when we try to generate data, they are very blurry. So I need to look at the literature again and propose something around it. And regarding the latent space that many people don't care much about it, probably they don't have sparsity that works. So they don't really know which latent dimension to look at. At the beginning, at the beginning of the thesis, when the model that didn't have still sparsity, when me myself I didn't even knew what sparsity was, I had to plot all the latent dimension one against the other to try to find which one is interesting, which one to look at to interpret. Probably it's because of that they are not interested in this. Because once you add the sparsity constraint, and the model tells you, look at this, and then in the order, look at this and that, it's very easy to spot stratifications. In my case, of course, it was also simple because we had target variable. I mean, we didn't use it to train the model. The stratification was still unsupervised, but the domain was already, let's say, the data were already favorable, I would say. So I think it's they don't look at it because they didn't have sparsity at work for them.
So this brings me to the very last question. I do think that the sparsity of the latent representation is a key contribution that you made. And what I was intrigued about is this statement that this approach allows you to automatically determine the latent dimension. And I have some doubts here.
Yeah,
because
you still need a threshold. You still need it.
Not only that, but when you showed on the presentation today and in one of the figure 2.7 in your manuscript, it's the same figure that you showed on the slides. Essentially, you say, I can use the negative lower bound as a way to find what is the optimal latent size, and you put it in red. I don't know. It looks like in some cases when you increase them dramatically the latent size, you still can get better results. So it's not optimal.
Yeah, yeah. It's a lower. It's not a model evidence. It's a proxy to the model evidence, and of course, in that case, it worked well because the data were simple. But we also have some cases where, let's say, I would call it an overfit, probably. Do you think it's an overfit? Because it may also be that.
I don't know if you can call it an overfit.
Because given that the data were generated synthetically with a linear model, and having this kind of behavior where actually with lower bound you end up overestimating the number of latent dimensions, I was thinking about the problem of overfit in those cases. And also of data quality, because when I separate, when I run the same experiment of data with a higher signal to noise ratio with a better quality, this problem is not there anymore. So I feel that the extra latent dimensions were just fitting the noise, and so this is why we had. Still, okay, it's not optimal as a way for model selection, but it's a proxy for it.
All right. It would be super nice if it went down and then up again, because then you can say it's optimal. Okay. Right now, fair enough, it's a proxy that you can use.
Anyway, that was without the sparsity constraint in action.
Okay, that's it for me. Thanks a lot for answering the questions.
Thank you. Then are there any other questions from the other members of the jury?
From other members of the jury? Well, there is the president is allowed to make questions. Right?
I will make a remark. I will make a comment.
No,
because I cannot make specific questions, I'm afraid. As the content is by far more complex than I can, deeply understand, as my colleagues did. And so I could not make competent questions, but I appreciate very much that in the introduction, you were able to, let's say, give a picture of the questions that these methods help addressing and how the different aspects answer to specific questions or tackle specific challenges. That was understandable also to me. And so I'm very thankful, and it has been very, very illuminating to follow. So when we think about data that need harmonization or that need compensating for missing data, you've always been, let's say, lucky enough to work with data that come from different research cohorts that might have, as you said, different observations or different protocols. So still elements are missing, but overall with, let's say, at least harmonization within the different studies. One might imagine, and I hope it won't be too far in the future, a use of digital health data that are not collected within research studies, but that are collected in clinical practice. As you all know, I mean, the practice in medicine has become digital, so data are available. Data are collected in a very disorganized way, with, I mean, systematically missing data. What is frustrating in following these type of presentations is that one has the impression that a lot can be done, but ultimately in the practice we do, still there is very limited access or no access at all to any kind of, I mean, strategies to learn or structure the data when they are generated in practice. So I was wondering if you have any comments on this, if you're thinking about future developments also to address these problems.
Well, thank you for this important practical insight. It's a very it's a big problem, this, because every hospital, I guess, that have its own information system, its own way on collecting data. So the harmonization there is can be hard to do. But with the within the context of the evidence-based medicine, I think that even if the hospitals are different, even if the clinical practice are different, there may be some biomarkers, some clinical evaluation that are very well standardized. So I would start from that, that kind of very well standardized measurement, and consider each hospital as a cluster, as a study by itself, and harmonize those kind of information. It's a hot topic, and I'm afraid I don't have the solution for that. And there are many teams actually working on it. And also, I think with a machine learning approach where they try to, for example, given a radiologic report to extract the key information out of it, or to simulate even further the imaging. I don't have a solution for that, but I know that there are people who can give it to you. Of course, there are people working on it seriously, and it's not as simple to solve.
I mean, thank you for your thoughts and your contribution. I think that's really, I mean, the direction we're going to. I loved in the concept of digital twin that you touched upon. I think that this is the way to go.
No, in
So
APON, we are very attached to the digital twins.
So, are there any other questions?
So maybe we could have Philippe, myself, and then Marco say a word.
Thank you, Nicolas.
I do not hear anything now. Possibly a microphone has been too, yeah, one has to stay on.
Is it better without the microphone? It's okay.
It's okay. So thank you, Nicolas, Mr. President. So I'm very happy to be here, even if I am not an expert in the field, but I think that it was interesting, and as a clinician, I find some of my baby in your first slide, and in the inclusion of clinical data, and also in your reference of your. So on the same time, it's not much on my side as a clinician, and on the other side, it's really on my side, because some of the topics you work on are really the problem of the clinician. I would like to say about heterogeneity of data, the problem of missing data. This is really important. This morning I was before your thesis in the daycare hospital, which is in Sophia Antipolis, and discussing with the professional caregiver about how to assess the fact that the care we provide to this patient help to stabilize 1 month, 2 months, and so on. And so this is not brain imaging data. This is very subjective and sometimes objective clinical data. And thanks also to add in your presentation the fact it's possible to use some kind of sensors in order to have objective data. So this caregiver this morning tell us that how to assess our feeling, even our subjective feeling about a patient, the way that he or she use his pen or his fork during the lunch. And what we know in clinics is that it is possible to have some kind of assessment of this. It's like the same question as for Twitter. I can give my inputs. I can say in clinic we call this ecological momentary assessment. That means that at one time I'm pushing on my phone and I say, are you happy to be at the thesis of which? Yes or no. So my question is, do you think that it will be possible in the future to use your type of model in order to use and to capture this type of clinical data? The second point, which is also related about this, and we discussed at the beginning of your thesis, is that most of the time, as clinicians, we have not so many data because in your work you use, for instance, the ADME or other big core data. In real life, the daycare center has not 100 patients. There is 25 patients. And so the other questions, and I don't know response, is it possible at one time to use also this type of model with a little amount of data?
To use with a little bit. To use it
with few data. If I'm working in my clinical practice with 20 patients, and I'm looking at it, do you think that this type of this is a real clinical practice? As a clinician, I have not 1,000 guys to look at the data.
Okay. So regarding the first question about the ecological measurement, I guess that the problem there is that these measurements are not standardized here. But at a certain point, there should be some way to standardize them. For example, about the I'm thinking about risk sensor, not talking about the movement of the day. There may be a partner, probably a regional partner, people on the Hôpitaux more because they are working. It would be interesting to have a way to collect this data from different regions and probably let's say we factorize out the geographic aspect, and so that it will be possible then to organize them based on just say daily routine around that. But of course, the way for doing it is for people to share the data. And this is a problem also of the team, because you have few data, but you would like to have more. So the way for making people comfortable in sharing data so that complex model can be trained is through what is called the federated learning approach, which is not my work, but there are people in the team working on it. It consists in gathering the data for yourself. You don't share your data, and so this solves also the issues of GDPR, for the consent, for the ethical reasons for which you cannot share your data. And at the same time, you learn a model out of that. So I think that learning from few data or learning from data that are not so standardized is made possible in the context of federated learning. Federated learning, yes, when you share, it was by, let's say, fitting locally a model and share the parameters with the other guy. So you're not sharing data, you're sharing just model parameters. And then there are different ways to compute the test parameters out of this collection. But this requires, I guess, I think the political will for doing it, because it requires infrastructures, data centers, and going to the public and say, look, you have to give your data, we are not using it. And I think already a big problem in the engagement of the people. For example, during COVID time in Italy, there is this application, or in France, Statistical. It's used to prevent the disease to spread. And the government were assuring people, we are not using your data, we are just doing it for you. But still, the engagement was very low. So I think it's possible to learn from free data, but ahead, way ahead, there should be a political will for doing it. So from a practical point of view, I think it will be possible. From a theoretical point of view, it's already possible.
Yeah. Unfortunately, we are human. So thank you, and I would like also to say thank you from Valeria Malera. Luckily, she is not here, but joined to me to thanks for the discussion and your interest for the clinic, and also because you help us to point with the joint model of heterogeneity, and you have a slide about this, and this is very interesting and very understandable for a clinician, and we share this with students. So thank you.
So Valentina, do you want me to say a word? Do you have to use this or not? You can hear me?
I can hear you very well.
Me to use this?
No, it's okay.
That's okay. All right. So I will have a question, but first I would like to say a few words. First of all, to thank the jury for all this hard work, and thank a lot Marco, who's supervised on a daily basis your work during all this period, and it has been a fantastic mentoring work. I would like to say also that your work is part of this, one of the very first projects funded by the Excellence Initiative of the University, the IDEX, in the project MNC3. MNC3 stands for something like cognition, behavior, brain measurements, and digital medicine. And it was really a nice way to bring together people from different worlds, of course, people from the hospital, people from the university, biologists also at IPMC, and of course, computer scientists and applied mathematicians at Inria. And we had two students. The first one defended last month, and you are the second one to defend. And it's really very nice to see all the work done during this project. And as was mentioned before, you've done both some methodological contributions. I didn't know it had influenced people in Pietro's group, But we can see with the citations of your ICML papers that some other groups also were influenced by this work. And of course, you've done an incredible experimental work. And we know that in this field, you have to really dig into the data. And I think you have an inclination for doing that in a very rigorous and very courageous also manner. So for all of this, I want to thank you very much. So I have a question, and this question raised after I asked a PhD student in our group to come and visit you to get some advice. Someone who is dealing with another type of images, ultrasound images, and having to combine information coming from clinical observations that we get on a written document, and of course, iconic information coming from the image. And I understood that the answer you gave was, oh, it's a bit different from my subject, I cannot help you. And I told the student, wow, it's not the answer that almost doctor in science should give you. So I am asking again the question, do you see a possibility to combine heterogeneous data like a written document along with an image as complex as an ultrasound image? Do you think there is something better than variational autoencoders, or do you think you could use something else?
This follows very well the answer, the question made from Pietro before. Why don't you use your method for some Twitter buzzing methodology where you can write something and generate gorgeous images? The problem is that with the variational autoencoder, the result that you obtain doesn't have the detail required by the, for example, the ultrasound images that are already noisy by themselves. So I don't think that with my frameworks this could be possible to do. Just for quality purposes, the quality that you would reach wouldn't be accepted for publication, right? It wouldn't make an impact. But probably by using some, for example, generative adversarial-based method with the modeling of heterogeneity, probably there is a chance to obtain results that have an impact.
Okay.
But it's a field that is new to me too.
Okay.
And no, I cannot tell what you cannot do with my method so far, and possible solutions that comes from the literature.
Okay. So sorry, I didn't want to make anybody uncomfortable about that. And of course, it was more on a very light manner that I was asking this question, just to see. Of course, problems that look very similar can in fact be very different, but it's very practical, and I hope we can get some inspiration also from the work you've done for this problem too. Okay, so I want to thank you again very much, and I want to apologize if I made anybody feeling comfortable about that. It was not the purpose of my question. Okay, I'm done.
Marco, you're the one who's next in line.
The very last. Can you hear me? Very good. Okay, so, well, Luigi, congratulations for making it to this point. I think this is the goal finally reached after such a long journey that started, I would say, 10 years ago when we first met. 11, maybe even worse. So time flies, actually. Yeah, 2011, 12, yeah. I made those numbers. Yeah. It's quite a while ago. We were both younger. I looked younger. You look almost the same. I looked much younger at the time. And yeah, no, many things happened in the meantime. We were both working for Giovanni's group in Brescia. So it was a different world, a different period. And I'm very happy actually that, yeah, that you were the first student I thought of when I had the chance to start something here in my new position. And it was a very important thing, and I'm very glad that you, at the time, you agreed actually to join and to start this part of the path together, to share this thing and to accept this challenge. That was not simple at the time. It was not simple for you. It was not simple for me either. So it has been, I think, very important to share this thing together. And I'm very happy that now we are here. After everything, it has been, complicated for many reasons. Many things happen in the world in the meantime. So the world is more complex than it was 11 years ago, I would say. But nevertheless, here we are. It's very nice. And I'm very happy also that today you had a confirmation of the quality of what you did and the importance of your work and the impact actually you managed to make with your with your PhD. You see that your work is a knowledge outside actually our circle of collaborators and community, outside our domain, which is a great thing for something coming from medical imaging, making it actually in other application domains and beyond knowledge elsewhere. I see constantly like the citation for your papers, and indeed, actually, thanks to your work, we managed to get out, actually being recognized for something that, well, was not really one of the main things of our group, which I think is really huge. And I'm talking about this, but so we had the example of Pietro, but there are many other groups and contexts that we had in the meantime. So I think this is very important. You're also the first student that managed to get a paper accepted to ICML, which is a very selective community, very selective conference, and is the primary venue for machine learning. And again, I think this is a huge goal. You paved the way for actually other stream of research in the lab, more oriented toward machine learning. And I think this is very, very important. So I would like you to really keep in mind that what you did is big. Is great, is solid, you deserve actually what you are getting, and also for the future, I hope, yes, that with this experience, actually you will make the right choice and you will go full speed actually onto, well, your career and, well, making use of at most of what I hope you managed to get and to learn from these past 4 years. These are 4, right? Yeah, okay. So that's everything. So thank you very much. And I don't have any questions. I think too many already in this last 11 years. So we can stop here.
Okay, thank you very much, Mark. It was very, very touching what you said. And I think I will, well, if I'm engineer behind it, you're the architect behind it. So what we've seen today, if it made an impact, I had a small contribution on it. I mean, I just follow your vision and try to follow you. So you were leading actually. I was just following, and this is the result. So I have many awards maybe for later, but for the moment, thank you for your nice words. Okay.
Thank you to Marco and Luigi for this very touching conclusion. I think that now is the time for the jury to discuss behind closed doors.
Absolutely.
So,
I won't be able to move. So
no, I will create what are called breakout
rooms. So we have to wait just 1 minute for the people to get off the room.
No problem at all. Thanks to all the public also for following.
Restez pas trop loin. Hein.
Il y a personne d'autre qui est connecté. Luigi, if you're about to leave the room, I think there's no need of breakout.
Except that we are on YouTube, non? Il y a un YouTube channel. Il y a 2000 personnes qui écoutent.
Par tweet, on va savoir.
So Luigi, are you staying with us?
So, no. Do you have the pop-up of the room or not?
Sorry?
Do you have the pop-up? Is there a pop-up for you to
No,
move?
there is no pop-up. No pop-up.
No.
We should receive. Yes. Now there is a pop-up to go in a private room. Okay. So everybody should go to the private room. Yeah.
Okay.
E per il volume parlare con Gloria e Valentina.
Ah voilà, ça y est, tout le monde est là.
Ci sono le costrade.
Ok, ça se fait que c'est mieux, oui. Valentina, you're muted. Yeah. Okay, very good. Gloria, can we hear you?
Yes, I'm here.
Perfect.
Okay. We are still streaming on YouTube.
So what do you want to do?
Maybe you should tell me.
On essaie de stopper YouTube.
We are still on YouTube, so we have to make sure. Sorry about that.
So is everyone in? Everyone seated?
Yeah,
Okay,
so.
Yes. So then, I mean, it's my great pleasure to have the, let's say, the responsibility to provide you with the results of the jury discussion. In order to keep it long a bit, so so that you suffer a few seconds more before knowing the results of our discussion, I'll follow on Marco's let's say speech to say that I had the opportunity to meet you, Luigi, many years ago in Geneva. So I'm very happy that after this time we have the occasion to discuss again for this very happy occasion. So the summary of the discussion of the jury work was that everyone was impressed by the quality, by the content, by the competence with which you presented your work, you defended your work in the debate and discussion with all jury members. So it's clear that we all unanimously agree that you obtain your degree, your PhD, with the mention très honorable. Excellent work.
Yeah.
Luigi, now some words from you.
Now the words from me. Well, it was a long journey, but at the same time, now it feels very short because it was for years, but some moments very tough and some moments very full. But I'm glad to be here today. And so, of course, this is not a solo journey. So there were many people involved, and this couldn't be possible without the contribution of many of them. And I want to thank them all. And I'm sorry that I have to read it because words are important and I don't want to forget anything, anybody, and also I don't want to get too emotional, so I will read it. So first of all, I would like to thank my supervisor, Nicolas AYACHE, for being actively present in all the most important moments of the PhD. I want to thank you for your scientific insights and writing advices, but mostly for the constant reassurance and encouragement that was actually very supportive. So thank you very much for this. Philippe, my other supervisor, and also I want to thank Valeria, both of you, for the insightful discussions about the importance of translating the research findings and taking into account the human clinical environment. So this is not an ivory tower, and we are going to, it is important to have in mind that we may have an important impact too. So thank you for this view, this enriching view. And of course, Marco, I just can't say you enough times thank you for your tireless scientific support over all these years, for your contagious enthusiasm, for believing it till the last seconds for the submission, for having taught me that hard work and attention to details eventually pays you back. And as I said before, you were leading all the time. I was just following. So what we've seen today is mainly also because of what you have done with me. So thank you very much for your support. I would like to thank the jury members here and online, in particular Professor Gloria MENEGAZ and Professor Pietro MICHIARDI for their voluntary contribution in reviewing the manuscript. Your comments and advices were very, I was surprising to seeing the report of someone who read about my work so in detail. So thank you very much for this. It's, I felt appreciated. Thank you. I equally advise the president of the jury, Professor Valentina GARIBOTTO, who accepted the role of examiner first and then presidency with joy and interest, as we have seen. So this PhD was for me an important journey, and I'm very happy for having shared this important journey with wonderful colleagues, ending up being dear friends, Clement, Jama, Sara, she's not here, Santiago. Few lines, few words here can express adequately my gratitude. So I will just say thank you very much for being my friends first. I want to say thank you to all the other members of the EPION team, from the PhD students, intern, postdocs, permanents, and the secretary that she's not here, but that she organized this day for us. So thank you to Isabel. And if you don't mind, I will switch to Italian now for the people online. Un grazie davvero molto speciale va a Silvia, grazie alla quale ho capito cosa vuol dire avere cura e impegnarsi per qualcosa di veramente speciale. Grazie, grazie di cuore. Le parole finali le riservo per i miei genitori, Antonio e Maria Concetta, che ci stanno seguendo, spero, per mio fratello Pierpaolo, per il loro costante supporto e l'affetto. È difficile essere lontani da casa, ma sapere che ho il vostro appoggio in ogni momento e che siete sempre lì per me, mi fa sentire al sicuro in ogni circostanza, quindi grazie di cuore a tutti. So thank you very much all, and it has been a pleasure for being with you.
Okay, so should we free now the jury?
Very moving closure. I mean, I complain a bit those who could not follow the Italian section, because this was also very personal and very touching. So congratulations once again, Luigi. Enjoy. Now it's time for celebrations. I'm very sorry I'm not there to be able to celebrate with you. I'm sure you'll have many drinks, and these are very well deserved. And I thank you all for the opportunity to join for this moment.
Thank you so much. Thank you very much. Thank you also to Gloria. And unfortunately, you won't be there for the drinks now, but
Yeah.
we share with you by.
Thank you.
There
will be another time. We think of you.
Goodbye.
But
Bye.
Pietro, we represent. Pietro, we represent you. Voilà.
Drink from us. Yes.
Thank
Ciao.
you. Bye bye.
you.
Ciao.
Bye.
Ciao.
Bye.
Grazie mille. Grazie mille.
Grazie.